And I'm back. If you're watching this in the classroom, then that means my dad had some difficulty regarding his surgical procedure, and I need to stick around for a little while longer. Okay? So anyways, this is chapter 6. We're finishing up on creating Lewis dot structures. I gave you a very quick crash course on that with your paper, and hopefully that made sense, but I'm going to go very quickly here with how to create these Lewis dot structures. Excuse me for a moment while I get water, and we're off, okay? You know Lewis dot structures are only made up of covalent bonds, okay? And typically we're talking about nonmetal atoms connecting with nonmetal atoms. That's pretty much it for it, okay? And it has to do with having 8 electrons in the valence shell, whether bonding or non-bonding electrons. Hydrogen definitely is an exception, okay? And the electrons are normally shared in pairs. Why? Well, 2 electrons of opposite spins occupy the empty orbitals. Now, polyatomic means you have more than one atom that are connected to each other. Now, when we talk about polyatomic molecules, have one or more central atoms bonded to surrounding atoms. Hydrogen cannot be the central atom. Why? Because hydrogen is too small. Now, carbon can be a central atom. We can look at silicon being a central atom. We can even look at aluminum or sulfur or oxygen being central atoms, okay? For examples. Now, how can we predict the number of valence electrons? All the nonmetals except the hydrogen can be predicted by the formula. Valence electrons is equal to the group number minus 10. Okay, so let's take a look at chlorine. Chlorine is in group number 17. 17 minus 10 is 7 valence electrons for chlorine. Now, in that previous video, I went ahead and I just did the quick and dirty version of, I gave you the dots. Here's the group, here's the number of valence electrons, bam. But this is a quick one. And again, this is for nonmetals. You cannot do this for transition metals because they have multiple personalities. Okay? Now, how can we predict the number of covalent bonds where the nonmetals are? Okay? Formula. Covalent bonds is equal to 8 minus the valence electrons. Now, we're looking at the number of bonds here, for example. Okay? So, how can we predict the number of covalent bonds where nonmetals are involved? Formula, covalent bonds is equal to 8 minus valence electrons. So, if we look at chlorine, chlorine has 7 valence electrons, so 8 minus 7 equals 1. So it can have 1 covalent bond to it, which would make sense. You can do it that way. If you look at oxygen with 6 valence electrons, 8 minus 6 equals 2. So oxygen can connect with 2. Now, can there be more bonds? Yes, but we're talking about naturally, okay? We can look at nitrogen. Nitrogen has 5 valence electrons, so 8 minus 5 equals 3, so nitrogen can normally connect with up to 3 other atoms. Carbon having 4 valence electrons, so 8 minus 4 is 4, so carbon can form up to 4 bonds, naturally. Okay, so moving on, steps for drawing the Lewis structures. Write the electron dot symbol for each element. Determine how many valence electrons are available. Place the element with the most unpaired electrons in the center of the structure. Okay? Now, if necessary, reposition the individual dots. Typically, when you're looking at the center of something, you're going to look for the atom that's got the most electronegativity. That's typically it. Okay? Place the remaining element symbols for the compound around the central atom, determining how many valence electrons are available. Create as many single bonds as possible by pairing up adjacent electrons. Create additional bonds if needed. Okay, check your structure by counting up the total number of electrons represented in the molecule. Okay, Excuse me. I pretty much did that with you guys. I just didn't do all the counting like they did. Okay, so for the electron dot diagram sheets, hopefully that you guys got those, you should have been able to do that. Okay, without it. Now, a polyatomic ion is a covalently bonded anion. It forms as certain elements with high electron affinities are part of a polyatomic molecule, and one or more of the missing valence electrons are filled by nearby extra electrons. Okay, that's nice. So, polyatomic ions. Inside the group of atoms in a polyatomic ion, like SO3, that would be a polyatomic ion example, okay? The bonds between the sulfur and the oxygen, they're covalent, okay? Now, it's ionic between the group of atoms and the atom or molecule bonded to the group, okay? It's a little bit different. Ionic between the group of atoms and the atom or molecule bonded to the group, okay? So, polyatomic ions often act as a unit. They typically stay together during the reactions. Okay? The charge indicates how many electrons the group loses or gains. Most are anions. So if we look at SO4 with a -2 charge, for example, okay, at this point, if we were to go and look at the sulfur and the 4 oxygens around it, okay, you're going to have to, in order to make things equal, that the sulfur has its 8 and oxygens have their 8, you have to add 2 electrons in there somewhere, okay? Now, as far as, do I know polyatomic ions that are positive? Well, yeah, there is an H4. That is a polyatomic ion, okay? That's there. Polyatomic meaning more than one. Okay, in this case, there's a cation ion here, round. And that's an NH4, that's ammonium, and this is sulfate. Okay? It's not working. All right, let's move on. Ionic bonding, now we're going into a new area. We talked about covalent bonding, where electrons are shared between atoms that are connecting to each other. But what about ionic? This is not ironic, this is ionic. Formed from a metal and a non-metal, you have a large electronegativity difference. Okay, so a metal and a non-metal. Think sodium and chlorine, potassium and chlorine. Okay, those would be examples of ionic bonds. Okay, the non-metal essentially steals the metal's valence electrons. In other words, you have an electron transfer. That's happening. Though you have a positive and negative ions attract. Well, if sodium loses its electron, chlorine now picks up an electron, okay, and we'll say it's from the sodium, then it's normal that they are going to combine together like this. This is ionic bonding, okay? There is no sharing of electrons. This is a question of, you have an electron, I want it. So, many of these ions clump together and they form a crystal. That's why a lot of ionic compounds, they tend to be crystals. Okay? Now, formula unit is the ratio of cations, not cations, Abe Cakish, to anions. Remember, cations are positively charged, anions are negatively charged. But I always remember the cations. So, calcium fluoride, each calcium atom in the compound gives its 2 valence electrons to 2 fluorine atoms, and it's a crystal lattice. Okay? Well, wait, what's a lattice? A lattice, it's an organization. It's a structure, if you will. If you go and build a house of Legos, there's going to be a certain structure that's there, because if you don't have it, you're not going to have a house of Legos. If you build a house in real life, there has to be a structure. There are frames. There are things that form walls and doorways and windows, those things. But think about it in the terms of like a crystal, okay? So when we look at it, there's metallic bonding. So let's go back here. Okay, so calcium fluoride, for example, so CaF2. That's what it would look like, okay? And sheesh, what in the world would that crystal lattice look like? Well, let's go with, I'm going to make it easy. A simple crystal like NaCl. So, what we would have here, we would have a positive, a negative, and a positive. So here's Na, here's Cl, here's Na. So what you would have, here's a positive, here's a negative, here's a negative. Okay, this would be an example of a structure, a lattice, if you will. And that's what they're talking about by crystal lattice. You say, well, wait, Canu, it's only, you know, two-dimensional, you got length and width. But the truth is, it is three-dimensional because you're going to have depth to it. Now, are all crystals the shape of a cube? No, they're not. And you'd say, but what makes the difference? It's the atoms that come together and they connect. Not all crystals are the same shape, which is kind of fascinating if you stop and think about that. Not all diamonds are the same. There are differences in there, in the diamond crystals, okay? Because there's color, and then there's the natural flaws that you will find in the diamonds, okay? But that's not an ionic thing. That's just the crystalline structure of the diamond itself. It's how those atoms are arranged. And this is what we are seeing here. This is an example of a crystal lattice. Now, if I were to go through and look at a crystal lattice, another way to look at it, if I look at it three-dimensionally, oops. So this is where you start looking at what does a crystal lattice look like. If I were just doing it with cubes like you're seeing there, I haven't done perspective in a while. That's one thing I took away from my 7th grade art class. Okay, so that's what we have when we talk about crystal lattice. Now what about metallic bonding? Well, metallic bonding, we've got to talk about the electron C theory. Very quickly, metals, when they bond together, there seems to be electrons that are just floating around in between them, in literally a virtual pool of electrons. But don't think of pool like very tiny. Think quite a lot. Think about it, you got all these electrons. And what does that do for the metal? Actually, it does some stuff. It does involve a rearrangement, an arrangement of metals in the form of a crystal lattice. Delocalized electrons. Oh, what does that mean when we say delocalized? The electrons are more free to move around from one orbital of atom A and go into an orbital of atom B. Whoa. Atom, orbital, what are you talking about? Remember, you have principal energy levels around the nucleus. And inside those principal energy levels, you have sublevels, right? Imagine electrons going from the sublevel of one metal atom, atom A, going into another sublevel of atom B. That's what they mean, that the electrons are more free to float around and be creative, if you will. So, here's an example of a crystal lattice, which I just showed, but this is a whole lot better. And I said sketch a crystal lattice. That you're going to need to spend a little bit of time on, okay? And I'm going to give you 5 seconds. Let me see how much time we have. Okay. We're winding it. Okay, I'm going to give you guys another 15 seconds. Hurry, hurry, hurry. Sketch, sketch, sketch. And we're moving on. Okay. Properties of compounds. Let's look at, this is our last section for chapter 6. And you kind of notice compared to chapter 4, 5 and 6 and 7, yeah, they go a little bit faster. So we are moving forward, okay? Properties of covalent compounds. Low melting point, because there's not that much attraction between the atoms. They're weak at best, okay? Think of butter, think of wax, okay? And even plastic, okay? They're not great for heat and electricity conductors. They're not good. They're not dense or hard necessarily. Sugar is another one that has a pretty low melting point. Okay, as you guys know, we can caramelize sugar. It's easy. Now, can we turn sugar into a form of a gas? No. Here's why. At that point, when you get the sugar to that temperature, the molecule itself is now breaking apart. It just is. Okay? That's just, you can't. All right, let's move on here. Network covalent substances. Covalently bonded into a three-dimensional network like diamonds. Silicates. Now, silicates are made of silicon. Okay? They're hard, they're brittle, they have high melting points, glassy lusters. In other words, they look like glass and they shine. That's the luster. The luster is the shine. Unusual electrical properties. That's another thing that we have here. Properties of ionic compounds. They're strong bonds, so they have a higher melting point, like salt. Okay? They're dense, they're brittle, they're hard. Now, they're good electron conductors if dissolved or they're molten, like salt. Liquid salt, okay, is a good one. Or if you dissolve salt in water, it makes a great conductor for the electricity. Okay? So, differences between covalent and ionic. Covalent, it can be hard and brittle. They do have, in this case, it's a network covalent. But your typical covalent substance, okay, your typical low melting point, okay? But when you look at something that's networked, okay, in a three-dimensional thing, like you're seeing for diamonds and silicates, that's opposite. Okay, and then properties of ionic, strong bonds, high melting points, okay, and as we wrap up, an alloy, our last thing here, is a mixture of two or more metals like wedding rings. So if you were to go and take the wedding ring, see like this one here, see that's a wedding ring, for those that you're wondering about it. Okay, it's an alloy, it's a mix of gold and silver, because gold by itself, pure gold, kind of falls apart more rapidly than, well, USC basketball defense. Okay, so properties of metals and metal alloys. Okay, they carry the electrical current and thermal energy. They're pretty good at that. They have a luster. The luster is the shine. How well does it reflect the light? Okay, they're malleable. We can hammer it. We can shape it. We can roll it. Okay, we can take metal, see this? That's malleable. This metal is malleable. We have been able to take it and be able to shape it and roll it. We've been able to shape it into a circle, we've cut it, we've shaped it, and we've made an invention out of it. Okay, it is also ductile. Ductile means stretched into a wire. Now, I don't know about the ductility of this particular metal item, and yes, I am hitting the bell to annoy you even more, okay? But ductile is stretched into a wire. And at this point, ladies and gentlemen, I am going to stop here. So, we finished off chapter 6, okay? We've talked about alloys, we've talked about ionic and covalent compounds. We talked about covalent compounds that are done in a three-dimensional network. Okay, we've talked about crystal lattices.